Hello everyone, welcome to the lecture again. In this last lecture, we are going to revise the key concept that we have learned in the dynamics part, that was the second half of this course. We started the discussion by looking at the Newton equation of motion in different coordinate system, namely the Cartesian coordinate, the planar polar coordinate, spherical coordinate and cylindrical coordinate system. So, in Cartesian coordinate, we have the x, y and z axis, and here this u1, u2 and u3 are the x, y and z, and the scale parameters h1, h2 and h3, they were 1, 1 and 1, and the equation of motion of the particle. So, let us say the particle is at point P and this particle is moving. So, in this case we saw that the unit vector does not change, it does not change the direction as the particle move from one point to other point, and the equation of motion was summation fx equal to m x double dot, summation fy equal to m y double dot and summation fz equal to m z double dot. In planar polar coordinate system, we have the r and theta coordinate. So, the particle moves. So, its position vector is r, and this r, the angle that it makes is theta. So, the unit vector along r is r cap, and in the perpendicular direction we have theta cap. So, here our u1 and u2 or the axis, they are r and theta, and the scale factors h1 and h2, they were 1 and r, and the equation of motion was summation Fr, this is the force along the r direction, that was m r double dot minus r theta dot square, and summation F theta was m r theta double dot plus 2 r dot theta dot. Now, note that in planar polar coordinate system, when the particle moves from one point to other point, in that case the unit vector also changes the direction. This was not the case in the Cartesian coordinate. Let us now look at the spherical coordinate. So, in spherical coordinate system, we have the r, theta and phi. So, let us say the position of the particle is P. So, that is defined by r, theta and phi. R is this r, theta is the angle that it makes from the z axis, and phi is the angle that its projection on the xy plane makes from the x axis. Okay. So, here our u1, u2 and u3, they are r, theta and phi, and h1, h2 and h3 are 1 r, r sin theta. Therefore, the equation of motion along the r direction, that is summation Fr equal to m r double dot minus r theta dot square minus r sin square theta phi dot square, summation F theta equal to m r theta double dot plus 2 r dot theta dot minus r sin theta cos theta phi dot square, and summation f phi equal to m r dot phi dot sin theta plus 2 r theta dot phi dot cos theta plus r sin theta phi double dot. In cylindrical coordinate system, we have r, phi and z. So, let us say this is x axis, y axis and z axis, then the position of the particle, let us say P, is defined by R, phi and Z. So, u1, u2 and u3, they are R, phi and Z, where R is the radius of the cylinder, Z is the height of the cylinder, and phi is the angle that this R makes from the x axis. Okay. And we saw that H1, H2 and H3, the scale factors were 1, R and 1, and the equation of motion in the r direction. So, summation f r was m r double dot minus r phi dot square, summation f phi was m r phi double dot plus 2 r dot phi dot, and summation f z was m z double dot. Then we looked at the principle of work and energy, and the equation we got by integrating the Newton's law with respect to displacement. So, principle of work and energy. So, we started with F equal to m a equal to m dV by dt. We integrated this with respect to displacement. Okay. So, we have integral f dot dr equal to integral m dV by dt and then dr, but then dr by dt is nothing but velocity. So, we have 1 to 2 f dot dr equal to m v1 to v2 v dv. So, we got u12 equal to m by 2 v2 square minus v1 square, or u12 equal to t2 minus t1, or in natural sequence we have t1 plus u12 equal to t2. Here t1 and t2 are the kinetic energy, the initial and the final kinetic energy, and u12 is the work done by the external forces. Okay. And if there are elastic members are also present, then it can be written as t1 plus v1 plus u12 equal to t2 plus v2. So, here V1 is the potential energy which include the gravitational and elastic potential energy, and U12 is the work done by the other forces. We also look at the impulse momentum equation. And the impulse momentum equation we got again from the Newton's law by integrating with respect to time. So, again we have summation f equal to m a, this was dp by dt, and we integrated this with respect to time. So, we got integral summation f dt equal to 1 to 2 dp, or t1 to t2 f dt equal to p2 minus p1, or in natural sequence p1 plus t1 to t2 summation f dt equal to p2. So, this equation tells that if the initial momentum is p1 and the linear impulse is this, then the final momentum will be p2. Then we studied the impact. Let us say I have two rigid bodies, then the tangent to the contacting surface is this, and the common normal to the surface in contact during impact is the line of impact. Okay. So, here in that common normal is this. So, therefore, this is the line of impact. Okay. We discussed two cases, one was the direct central impact So, herein the velocity of the bodies are directed along the line of impact. So, that means if this is the line of impact, then the velocities are along it. Let us say the velocity of this body is V A, the mass is m A, and the velocity of this body is V B, mass is m B. Then for the impact, V A has to be larger than V B, and after the impact the velocity of body A is, let us say, V A prime, and the velocity of body B is V B prime. Then the question was, what are these velocities? And for that, because there are two variables, we need two equation, and one equation comes from the definition of coefficient of restitution. So, we got E equal to V B prime minus V A prime over V A minus V B. So, this E was the coefficient of restitution, and V B prime minus V A prime is the relative velocity of separation of the bodies, and V A minus V B is the relative velocity of approach. Okay. And the conservation of linear momentum for the whole systems gives us. So, this comes from the second equation, comes from the conservation of linear momentum of the system. So, we have m A V A plus m B V B equal to m A V A prime plus m B V B prime. So, we have two equation and two unknown. So, therefore, the problem was solved. Then we look at the oblique central impact. So, herein we have, let us say, two bodies, and the line of impact is this. Okay. And let us say the velocity of body A is V A and the velocity of body B is V B. Then the question was, after the impact, what is the velocity of the bodies? So, let us say this is V B prime, this one is V A prime, and the directions are also involved. So, there were 4 parameters, 2 for the velocity and 2 for the direction. Let us say the direction of the tangent to the contacting surface is T, and the direction of the line of impact is N. In that case, we have in the N direction we have E equal to V B prime N minus V A prime N over V A N minus V B N, and we have the conservation of linear momentum for the whole system. So, this is the same case as before, m A V A N plus m B V B N equal to m A V A prime N plus m B V B prime N. And then two equation comes in the T direction. So, we have in T direction, since there is no impulse, so therefore, the momentum of each particle remains conserved. So, we have m A V A T equal to m A V A prime T and m B V B T equal to m B V B prime T. So, we have 4 equations and 4 unknown. So, again the problem is solved. Then we discuss the variable mass problem. So, herein we consider a system which is either gaining the mass or losing the mass. To formulate the problem, we said, well, let us say there is a small mass dm which is moving with a velocity v naught, and we have a bigger mass, let us say it is denoted by m, moving with a velocity v. Then at time t, this is the initial case, and then after they combine together, then we have the mass m plus dm, and the velocity is v plus dv. Then we use the impulse momentum relation to find out the equation for the variable mass problem, and it was m dv by dt equal to f external plus dm by dt into u rel, where this u rel was v naught minus v, or the velocity of the smaller mass minus the velocity of the bigger mass. Then we look at the moment of inertia. The moment of inertia of a body is defined as I equal to integral r square dm, and then we look at parallel axis theorem. So, suppose I have a rigid body, and we have an axis which is passing through the center of mass, let us say g, and let us say this is b prime, and we want to know what is the moment of inertia of this body about a prime axis, which is parallel to b prime and at a distance of d. Then the moment of inertia I about a prime is I bar plus m d square. Here I bar is the moment of inertia about the center of mass axis. So, this is about b prime, and I is the moment of inertia about a prime, which is an axis which is parallel to b prime and at a distance d. Then we discuss the perpendicular axis theorem. We said, let us say there is a body which is in 2 dimension, and let us say in the xy plane, and then we want to calculate the moment of inertia of this body about the z direction. Then the moment of inertia about z is Ix plus Iy. Then we discuss the moment of inertia of composite bodies. Let us say I want to calculate the moment of inertia of this object about OO prime, then the moment of inertia of this object will be, let us say this is object 1, 2 and 3, then the moment of inertia about OO prime will be the moment of inertia of the first object plus the moment of inertia of the second object plus the moment of inertia of the third object. Mathematically I can write down as I, the moment of inertia of the composite body, equal to the moment of inertia of all subparts, and then sum them together. Herein we have to note that the moment of inertia of all subpart, it must be calculated with respect to the same axis, here OO prime. Then we look at the moment of inertia of the rigid body about an arbitrary axis. So, let us say I have a rigid body, and we have the x, y and the z axis, and I want to calculate the moment of inertia about, let us say OL. Then we saw that IOL was Ixx L square plus Iyy m square plus I z z n square minus 2 I x y L m minus 2 I y z m n minus 2 I z x L n. So, here I x x is the moment of inertia about the x axis. Herein we encountered I x y, I y z and I z x, these are the product of inertias, and the inertia matrix I is defined as I x x, I y y, I z z, then we have minus I x y, minus I x y, minus I x z, minus I x z, minus I y z and minus I y z. Then we discuss the principal axis of inertia. We saw that if we examine the rigid body and its moment and product of inertia for all possible orientations, then there is always an orientation for which the product of inertia vanishes, and in that case I becomes I 1, I 2, I 3 and all the product of inertias are 0. Okay. So, here this I 1, I 2 and I 3, these are called the principal moment of inertia, and this x, y and z axis for which all the product of inertia vanishes, they called the principal axis. We then discuss the plane motion. And we saw that a rigid body execute a plane motion when all parts of the rigid body they move in a parallel plane. Particularly we discuss the general plane motion, and this general plane motion is the combination of a translation and a fixed axis rotation. So, let us say I have a rigid body, and let us say there are 2 points on the rigid body B and A, and this body performs a general plane motion. So, the general plane motion can be analyzed by considering it as a combination of the translation of let us say the point B and a fixed axis rotation of point A with respect to B. The relative velocity of point A will be the velocity of B plus the velocity of point A with respect to B. Now, since point A is making a fixed axis rotation about point B, therefore, VAB will be omega cross r, and the relative acceleration of point A will be the acceleration of point B plus the acceleration of point A with respect to B. Now, AB has two components, the normal component and the tangential component, because this is making a fixed axis rotation. So, we have the n component and the t component. So, therefore, AA will be AB plus AABN plus AABT, and the value of the normal acceleration in fixed axis rotation is v square divided by r, or r omega square, where r is this distance. And AABT is R omega dot or R alpha. We then discuss the general equation of motion of the rigid body. Let us say I have a rigid body and on this rigid body various forces are acting. And G is the center of mass, then this situation can be analyzed by replacing all the resultant forces at some chosen point. So, let us say the chosen point is Z. So, as if at G all the forces are acting and then there is a corresponding couple or the moment about the mass center G. And then we can write down the equation of motion. So, we have translation equation of motion which is summation f equal to m a bar, where a bar is the acceleration of the center of mass, and then we have a rotation equation of motion which is summation mg equal to lg dot, where L is the angular momentum. So, because of this we have m a bar and because of m there is lg dot. We then looked at the work energy and impulse momentum relation for the rigid body. And we saw that their form remains the same as they were for the particle. Herein we have the work energy equation as T1 plus V1 plus U12 equal to T2 plus V2, and the kinetic energy T1 is half m V1 square plus half I omega 1 square, because the body has also the rotational energy. And the impulse momentum equation was L naught 1 plus integral T1 to T2 summation m naught dt equal to L naught 2. Here L naught 1 is the initial angular momentum and integral m dt was the external angular impulse, and L naught 2 is the final angular momentum. Finally, we discuss the Euler's equation of motion. So, we said that suppose I have a rigid body and capital X, capital Y and capital Z are the fixed frame, and small x, y, z are the rotating frame which are fixed with the body. So, basically they are the body frame, and if this small x, y, z are also the principal axis of inertia, then we have the equation of motion of the rigid bodies as summation mx equal to ixx omega x dot minus iyy minus izz omega y omega z summation my equal to iyy omega y dot minus izz minus ixx omega z omega x summation mz equal to izz omega z dot minus ixx minus iyy omega x omega y. Well friends, with this we come to the end of this particular course on mechanics. I hope that this course was useful to you and you were able to learn and understand various concepts related to Newtonian mechanics. I understand that there is always a scope for improvement in teaching, and therefore I look forward to get valuable feedback from you so that we can make it better with time. Taking this course under the NPTEL platform was also a learning experience for me, and I am very grateful that I got this opportunity. I thank the TA Nikita Chaudhary and Diksha Sharma for helping me throughout this course. I hope to see you next time, probably with a different course on physics. Thank you.